So matrix multiplication is a little bit different than matrix addition or even just regular multiplication, even though we use multiplying of integers here when we look at multiplying with matrices. So because a matrix is an array of numbers, when we multiply matrices together, we're going to multiply rows by columns. So there's a rule that we have to follow that you can only multiply two matrices together if the number of columns in the first matrix is equal to the number of rows in the second matrix. And the easiest way to check that is to take and write out the dimensions for each matrix. So the first one there is a 2 by 3. The second one is a 3 by 2. And check your inside numbers when you write it in this order. Those two numbers must be the same because I have to have the same number of columns as rows in order for this operation to work. The other thing is knowing the size of the result of the matrix. You determine the dimensions of the matrix by those outside numbers. So in this case, our matrix multiplication would result in a 2 by 2 matrix. And I know that sounds a little bit weird because you're thinking, well, we've got 3 numbers there. How am I going to end up with only 4 total entries? And again, that's because the process is not just a simple one-to-one multiplication. We're going to have to multiply entries together, and then we combine them by addition to create a single number. So for example, we have a 2 by 2 being multiplied by a 2 by 3. And we're going to multiply the first row by the first column. And then those numbers are going to get added together. So we're going to multiply 2 by 3 and negative 1 by 5, and those get added together. We then take and multiply the first row by the second column, and that goes in the first row, second column of the solution matrix. So 2 by negative 9, negative 1 by 7, and add them together. And then the first row, third column in the solution matrix is found by multiplying the first row by the third column of the two matrices being multiplied together. So our entry here would be 2 times 2 added to negative 1 times negative 6. So we follow the same pattern for the second row, but now we're going to multiply the second row by each column and then add. So 3, 4 multiplied by 3, 5 will give me the second row, first column in the solution matrix. So 3 times 3, 4 times 5, and add them together. Again, we move to the second row, second column. So we're multiplying 3 by negative 9 and 4 by 7. So the last step is to multiply the second row, third column together. So 3 times 2 and 4 times negative 6. Our answer, then we simplify all of this together. Would be a 2 by 3 matrix, 1, negative 25, 10, 29, 1, and negative 18. So for number 2, we have a 2 by 3 and a 2 by 2. So when we take and look at those dimensions, the problem that we run into, again, is our inside numbers of 3 and 2 do not match, which means that these two matrices cannot be multiplied together. So our solution would be that that operation is undefined. So for number 3, we have this nice equal sign here. So what we're thinking about is what would happen, what would be the result if I multiplied all of these things together, and then what does this 1, 7, and 8 result in this final multiplication? If you think about multiplying that first row by the first column, we would have 1x, 2y, and negative z. Because of like terms, I can't add those together. I would leave that as a single expression, but then I would say that it's equal to 1, which is the first row of our solution matrix. So the second row would be 1x plus 3y times 2z is equal to 7. And the last one would be 2x plus 6y plus z is equal to 8. So we have a system of equations with 3 variables and 3 equations, which is what we're going to be looking at learning how to solve with matrices starting in our next lesson. So for number 4, we have a 2 by 2 being multiplied by a 2 by 2, which means they can be multiplied together, and the result is going to be a 2 by 2 matrix. So for the first column the first row multiplied by the first column, I would multiply 0 times 4 and negative 1 times 2. For the second column in the first row, we would multiply 0 times negative 3 and negative 1 times 5. In the second row, first column, we multiply 1 by 4 and 0 by negative 2. In the second row, second column, I multiply the second row 1 times the second column, negative 3, and add it to 0 times 5. So for my final solution, when I simplify all of those, it would be 2 by negative 5, 4, and negative 3. So if you're not sure about what rows and columns to multiply together, one thing that I like to think about are these entry numbers and thinking about these subscripts. So this number is telling me the row of the first matrix that's being multiplied by the column in the second matrix. And again, that just kind of helps me keep it straight in my head and know what things are being multiplied together to create those entries. So for multiplication, one thing that we also want to think about is what happens when I'm multiplying things together in a context. So here we have 2 uniform suppliers here. We have your sizes of uniforms here. Again, we have sizes, and then we have team names. So the teams are trying to figure out how much it's going to cost for them to purchase these uniforms. So if I was just going to calculate without using matrices, I would say, well, I need 6 uniforms at $28 for everybody that needs a size small. And then I'm going to add that to the 11 uniforms that I need in a size medium. Those are going to cost me $36 a piece. And then for the large uniforms, I need 3 of those at $41 a piece. And I would add that together and they would give me the total that would cost for uniforms plus. And then I would also do the same thing for sporting supplies, and then I could compare the two totals and figure out how much it was going to cost for me to purchase these uniforms. Now, if I have this set up in a matrix, what ends up happening is that it's giving me the teams across the top and the suppliers in the rows, so that I can very easily compare dollar amounts to purchase from each supplier and which one is going to be more affordable for each team. So we still follow the same multiplication that you see here, but now they're just being entered into those elements or entries inside of the matrix. So as we talked about with addition, we do have some rules that we have to think about and follow for matrix multiplication. So matrix multiplication is only defined when the columns in matrix 1 are the same number of rows in matrix 2. Matrix multiplication is not commutative. I cannot change the order of two matrices and be able to get the same result. Because if I had a 2 by 3 and multiplied it by 3 by 4, that operation can be completed and it results in a 2 by 4. But if I were to switch the order and make it a 4 by 3 multiplied by a 2 by 3, these are not the same, which means it is undefined operation. So be very careful with your matrix multiplication. We can't just change the order in order to multiply two matrices together. So for a multiplicative identity, that means that we want the output to be the same when I multiply by whatever this matrix is. So something that's going to give me what I started with. So that's the identity matrix. So the identity matrix is a square matrix, which means the number of columns and rows has to be the same. If this was a 2 by 2, we put ones in what's referred to as the main diagonal. So it could be a 3 by 3 with 3 ones. It could be a 4 by 4 with 4 ones. It doesn't matter. And then we fill in zeros with everything else. So if I were to multiply by the identity matrix, again, the result would be the same as what I started with. So multiplicative inverse is your undoing operation. Now, we don't have division by a matrix. We just have the inverse. And so if I take and multiply matrix A by its inverse matrix, and again, that looks like an exponent to the negative 1. Remember, that's your inverse notation. We would have a result of 1. We're not going to find multiplicative inverse for matrices by hand. We are only going to be doing that on the calculator in this course, and we'll be looking at that more when we look at systems of variables. So that's everything that we need to know for matrix multiplication. Again, it just takes practice and thinking about what things are being multiplied together to generate the solution matrix.